All right. Good morning, everybody. So today is our final lecture for the semester. So thank you very much for being present during the lectures. Um, about the final exam, we will have our final exam next week, and it's scheduled for Tuesday morning. I posted the instructions on Canvas. If you have any questions, you can email me. And I also posted a Zoom link where I will be available during the final exam. So if you have any questions about any of the questions in the final, then just use the link and then you can ask me if you have questions regarding uh, the exam. Okay, so for today, we have on the schedule chapter number 10 and chapter number 11. Both chapters are very, very short. And those chapters are the chapters that we have the opportunity to use all the knowledge that we have acquired during the semester. Okay, so with that being said, so see, let's start with chapter number 10. Start my screen share with you. Okay, so chapter number 10, we will talk about intermolecular forces. Okay, so the forces that keep everything together. So intermolecular forces will explain why some compounds are, for example, in the solid state, liquid state, or gas state at room temperature, for example. In this chapter, of course, we will cover the different types of intermolecular forces, and we are also going to correlate intermolecular forces with boiling point and also polarity with solubility. Okay. With that being said, so let's start here. So the first intermolecular force that I will present you is called dispersion or London intermolecular forces. Dispersion forces are predominant are the predominant intermolecular interaction between two or more nonpolar molecules. Okay, so this is where dispersion forces will have a high influence when we have the interaction between two or more non-polar molecules. The dispersion forces are based on the creation of induced dipoles due to the uneven movement of the electron cloud. So we will cover that in a few minutes. It is a very weak interaction. And another name for dispersion forces, they are also called van der Waals interactions. Okay. So as an example of dispersion forces, I would like to show you the chlorine molecule and also the iodine molecule. So to do that, I will change to my other screen here, and then we can do some notes as well. All right. Okay. So first things first, every time you have nonpolar molecules, you will have dispersion forces as your predominant intermolecular interaction. And those are the forces that will keep the bulk material together. They are very weak intermolecular forces, and they are based on the creation of induced dipoles. Okay, so let's see how that works. So starting here with the Cl2 molecule, okay? Of course, because you have two chlorine atoms bonded in a linear fashion, the resulting magnetic dipole moment of this molecule is zero. Therefore, this is nonpolar. And therefore, we have dispersion forces as the predominant interaction. How does that work? If we could take a picture of the electron cloud for the chlorine molecule, we would see something like that. Okay, so you have something like that. And it's a pretty even electron cloud. However, this is not ideal, and each chlorine are battling for electrons, okay? So although they have the same electronegativity, in a split amount of time, this electron cloud is shifted towards either the left side or the right side. So this shift in the electron cloud will create a very, very small dipole moment. So we can have something like that. Okay. So in a given moment, we have an accumulation of electron cloud in the chlorine on the left side, and that creates a very tiny dipole moment. Remember that dipole moment or electron density I'm going to represent as the delta. The points where there is an accumulation of electron density will get a delta minus, and of course, the other side has to be a delta plus. Okay, so for a split amount of time, we have a very small polarization in the molecule. This very tiny polarization will attract another molecule where we also have a tiny polarization, and the same thing for the other side. Okay. So these very tiny flotations of the electron cloud will result in a tiny polarization of the molecule that will attract another molecule. And those are called the dispersion forces. Of course, larger the molecule, higher the probability of moving the electron cloud towards one or another atom. So that will result in a more intense dispersion force. And that's why Cl2 is a gas at room temperature. However, iodine, I2, that is a solid at room temperature. Okay, so the molecule of iodine is larger because iodine is larger than chlorine. Therefore, it's easier to create this polarization in the electron cloud. Therefore, the dispersion forces are more intense. Okay, so now let's move on to polar molecules. What are the possible intermolecular interactions when we have polar molecules. So we will start with the dipole-dipole forces. It is an intermolecular interaction between two or more polar molecules. This kind of interaction is based on the interaction between the dipoles of polar molecules, and it is a moderate to strong interaction. Let's see as an example the molecule dimethyl ether. Dimethyl ether has an oxygen at the center of the structure, and this oxygen is bonded to two methyl groups. Okay, so methyl group on the left and methyl group on the right side. If we take a look at the polarity of the carbon-oxygen bond, we will figure out that this bond is polar and it points towards the oxygen because oxygen is more electronegative than carbon. Therefore, oxygen will pull closer the electron pair being shared in this covalent bond. And the same thing on the other side. Because the molecular geometry is bent, that creates a resulting dipole moment different from zero, which means the molecule is polar. Okay, so for the dimethyl ether, we have an accumulation of charges localized on the oxygen. If there are accumulation of charges, we represent that as delta minus, and that creates a delta plus on the methyl groups. Okay, so therefore this molecule is polar and it's polarized. Okay, on the oxygen we have an excess of electrons, and on the carbons we have a deficiency of electrons. So this creates a pole in the molecule, like a small charge, and this polarization will attract the opposite sign. So the part of the molecule that's positive will, of course, attract the negative part of another molecule. So here delta minus, delta plus, and delta plus. So this will attract another molecule here. The same thing on the other side. So delta minus, delta plus, and delta plus. And here the same thing if we go to the bottom. Delta minus, delta plus, and delta plus. So that will attract here, and that will extend towards the whole compound. Okay, so that's how dipole-dipole forces work. Because you have a very defined polarization in the molecule, this kind of interaction can be classified as a moderate to strong interaction. Okay, so remember that dipole-dipole forces will exist when we have the interaction between two or more polar molecules. And this interaction is based on the dipole moments of the molecule. The region that there is an excess of electron density is labeled as delta minus, and the region where there is a deficiency of electrons is labeled as delta plus. Okay? Delta minus will attract delta plus and vice versa. And that's the interaction that will keep polar molecules together. Okay, so second kind of interaction when we have a polar molecule, that's a very special interaction called hydrogen bonding. It is an intermolecular interaction between two or more molecules where there is hydrogen bonded to fluorine, oxygen, or nitrogen. It's a very specific case, and we must have hydrogen bonded to fluorine, oxygen, or nitrogen. It is based on the interaction between strongly positive charged hydrogens and strongly negative charged fluorine, oxygen, or nitrogen. Because the charges are very, very strong, hydrogen bonding is a strong interaction. As an example, I would like to show you the water molecule and explain how hydrogen bonding happens. Water molecule, very simple, H2O. The molecular geometry for water is bent shaped. Okay. Remember that the most electronegative atom is fluorine. That's followed by oxygen, nitrogen, chlorine, bromine, iodine, sulfur, carbon, phosphorus, and hydrogen. Okay, von Clebrich pH. This is the most electronegative atom. Okay, so look here. Note that the electronegativity difference between fluorine, oxygen, nitrogen, and hydrogen is huge. Therefore, it's not even fair for the hydrogen. When hydrogen is bonded to fluorine, oxygen, and nitrogen, the electron pair is almost all to those three elements. Okay, so it's very, very close to fluorine, oxygen, or nitrogen, and very far from the hydrogen. So because the charges are so split, that creates a very strong dipole, sorry, a very strong accumulation of the electron cloud on the oxygen and a very strong deficiency of the electron clouds on the hydrogen. Okay, so the huge electronegativity difference when we compare fluorine, oxygen, and nitrogen with hydrogen will create very strong poles in the molecule. And again, we have a strong negative polarization on the oxygen and a strong positive on the hydrogen, and those poles will attract the opposite sign, and that's what will hold the molecule together. So then we will go from here, and this will extend towards the space. So hydrogen bonding, you can think as a very uh, extreme case of dipole-dipole interaction. And remember, the first criteria, we have to have a hydrogen bonded to fluorine, oxygen, or nitrogen to create this very strong polarization. And this hydrogen will interact with fluorine, oxygen, and nitrogen bonded to hydrogen. Okay, so here we have a very strong positive pole interacting with a very strong negative pole. This has to be clear. First, hydrogen needs to be bonded to fluorine, oxygen, and nitrogen, and this hydrogen will interact with fluorine, oxygen, or nitrogen from another molecule that has to be bonded to hydrogen. And this is the hydrogen bonding, a strong interaction. Okay, so we started with dispersion forces. That is the intermolecular interaction when we have nonpolar molecules, and it's based on the short creation of dipole moments in the molecule because of the movement of the electron cloud. Then we moved on to the dipole-dipole interactions, which is the predominant interaction when we have polar molecules, and that's based on the polarity of the molecule. Then we moved on to hydrogen bonding, which is the interaction between a hydrogen and fluorine, oxygen, or nitrogen. And because the electronegativity difference between fluorine, oxygen, and oh, sorry about that. Fluorine, oxygen, and nitrogen compared to hydrogen is huge. That creates almost a positive charge on the hydrogen and a negative charge on fluorine, oxygen, or nitrogen. Okay, so see that we started with a weak interaction where there is barely charge. And as we are moving on, we are moving towards the creation of a charge, a de facto charge on the atoms. So let's scale up. So let's move on. And now let me present you the ion dipole forces. It is an intermolecular interaction between a polar molecule and an ion based on the interaction between dipoles and ions. Ions can be cations or anions. It is a strong to very strong interaction. As an example, I would like to show you what happens when sodium plus is dissolved in water. Okay, so let's start here with sodium plus. So that has a very well defined positive charge. And we know that the water molecule is a polar molecule where there is accumulation of electrons on the oxygen. So therefore it creates a negative pole in the molecule. And therefore we have a delta plus on the hydrogens, okay? So deficiency of electrons. Because sodium is positively charged, that's going to attract the negative side of the water molecule. So when we dissolve sodium plus in water, sodium plus is capable of organizing water around it, and it's going to attract the negative part of the water molecule. Therefore, all the oxygens will turn their attention to the sodium plus, and they want to be really close to sodium plus. Okay, so all the water molecules will compete for the attention of the sodium plus and will be all over the sodium plus. And this is called ion dipole interaction. Because the ion is a charge attracting a polar molecule, this is going to be a strong to very strong interaction. Okay, so is there an intermolecular interaction that's stronger than ion dipole? So the answer for that is yes. If we have an ion interacting with another ion, that's the strongest intermolecular interaction that we can have. Ion-ion forces are an intermolecular interaction between two or more ions. Is based on the interaction between, of course, ions that can be cations interacting with anions and vice versa. And because we have two charges, this is a very strong interaction. For example, here, let's talk about sodium chloride. Sodium chloride to start with, it is an ionic compound because we have an element that wants to lose electrons, therefore becomes positive, which is sodium, and another element that wants to get one electron and therefore becomes negative, which is the chloride, okay, Cl minus. In an ionic compound, we always have a positive and a negative charge. So if we would have to represent that, we have here sodium plus, and sodium plus will attract chloride or Cl minus. See here that I intentionally draw sodium plus as a small ion and chloride as a large ion. That's because when sodium loses an electron, it shrinks, and when chlorine gains an electron, it increases its radius. Now, of course, the positive charge of the sodium will attract the negative charge of the chloride ion, and this kind of interaction is labeled as ion-ion forces. It is a very strong interaction because we have a positive charge attracting a negative charge. And that's going to rank at the top of the intermolecular interactions. Okay, so this is the strongest interaction possible. Okay, so let's summarize what I told you. Okay, so here we have a figure. The first column in this figure names the type of force or intermolecular interaction. We have a rank and an example when that happens. Okay, so we started with dispersion forces or London forces, or also called van der Waals interaction, based on the creation of tiny dipole moments because of the electron cloud movement. Then I showed you the dipole-dipole interaction that happens when we have two or more polar molecules interacting. Then hydrogen bonding. Okay, so hydrogen bonded to fluorine, oxygen, or nitrogen. And then ion dipole, okay, an ion interacting with a polar molecule. And it is not in this figure, but higher than that, we can have the ion-ion interaction. And from bottom to top, the second kind of interaction that I haven't talked yet is called dipole-induced dipole. So let's talk a little bit about this kind of interaction that happens when we have a non-polar molecule interacting with a polar molecule. So what happens here? So let's, for example, use the example here. What happens when we have water interacting with oxygen? Oxygen is a nonpolar molecule, so therefore we have an even distribution of the electron cloud. However, water is a very strong polar molecule. What's going to happen here is that because water is has a very strong polarization, that will induce the polarization in the nonpolar compound. So for example here, the hydrogen that's very uh, strongly positive, that will attract the electrons towards the left side of the oxygen molecule, and that will create a distortion in the electron cloud of the oxygen molecule. So that will pull all electrons here towards the left side, and that will create a dipole in the oxygen molecule. Okay, so that's why this interaction is called dipole induced dipole. It happens when we have a polar molecule interacting with a nonpolar molecule. Because of the polarization of the polar molecule, that will distort the electron cloud of the nonpolar molecule and create an induced dipole. The strength of this interaction is the intermediate between dispersion and dipole-dipole. All right. So as I told you, we can use the intermolecular interactions to explain, for example, melting point and boiling points. The melting and boiling points are directly correlated with the intermolecular forces. Stronger the interaction, higher the melting and boiling points. For example, the boiling point of water is 100 degrees, while the boiling point of H2S is minus 60 degrees at sea level. Why such a difference? We have basically the same formula, same molecular geometry, same group. Why such a huge difference? So let's analyze the intermolecular interactions in the two molecules. And higher the interaction, that will result in an elevation of the boiling point. For water, as I showed you, we have oxygen bonded to hydrogen, so that creates a very strong polarization. And this oxygen will interact with the hydrogen of a neighbor molecule. And this kind of interaction is called hydrogen bonding. Remember, we have to have oxygen bonded to hydrogen, or fluorine bonded to hydrogen, or nitrogen bonded to hydrogen, interacting with another hydrogen that is also bonded to fluorine, oxygen, or nitrogen. Okay? Hydrogen bonding is a very strong intermolecular interaction and will keep the molecules closer. If we take a look at H2S, we still have a polar molecule. However, now is sulfur bonded to hydrogen, so that does not polarize, does not strongly polarize this bond. This molecule is still polar, so that creates a delta minus and a delta plus that will attract the opposite sign of a neighbor molecule. Now, in this case, the interaction is a dipole-dipole interaction. This interaction is weaker than hydrogen bonding, therefore it's easier to break the interaction and then move the compound, for example, from the liquid to the gas state. And that is the reason why water has a higher boiling point than hydrogen sulfide. Okay? See the huge difference that a hydrogen bonding makes when compared to dipole-dipole. So the difference in the boiling point is around 160 degrees. So always start thinking about intermolecular interactions to explain melting and boiling points. Another area that hydrogen bonding is useful is in biological systems. And I'm highlighting here the DNA. So the DNA is formed through the interaction of the nucleobases or nitrogenated bases. We have T, C, A, and G. Okay. So note here that in the structure of the nitrogenated bases, we have usually an NH2 group, so nitrogen bonded to a hydrogen. And this is a potential to interact with another base through a hydrogen bonding. And that's how the DNA is held together. Okay. So we have here, for example, the interaction between adenine and thymine. If we look here, we have nitrogen bonded to hydrogen for the NH2 group. So we have a strong polarization of the bond that creates a very strong delta minus and delta plus, and this is capable to interact with another NH from a neighbor base, for example. Oops, sorry. Delta plus, oh, delta minus and delta plus. So that will create a hydrogen bonding. And the hydrogen bonding is the major intermolecular force that keeps the DNA together. We also have dipole-dipole interactions, but hydrogen bonding is one of the most important interactions in this case. Okay, I didn't put here, but especially in biological systems, there is another kind of interaction called sulfur bonding, oops, or also called sulfur bridge. Sulfur bonding happens in your hair. Okay, so your hair is coated with a protein that has a lot of sulfur atoms exposed, and the sulfur atoms will interact through a sulfur bonding. Usually, people with curly hair, they have more sulfur bonding interactions when compared with not curly hair. Okay, so these interactions will twist your hair. So when you go to the hairstylist or the hair salon to get your hair straightened, the first part is usually a chemical treatment that they call. So the chemical treatment will zip this sulfur bonding and split them apart, and then you straighten the hair and redo the sulfur bonding in a way that your hair gets straightened. Okay, and that is also an intermolecular interaction. Okay, so let's move on back to the PowerPoint. Right. Okay, and because water has very strong intermolecular hydrogen bonds, it has a very high surface tension, and this surface tension is so high that it can support small insects on the surface. Okay, so these insects, they spread the pressure apart, and they are capable of float in the water because of the hydrogen bonds. Okay, so imagine hydrogen bonding as a network, and this network will support the insect at the water surface, and because it's strong, it can hold this animal. Okay, so another example of intermolecular interactions is the ability of some lizards to walk on the walls. As the friction between the toes and the surface of walls creates van der Waals interactions or London forces or dispersion interactions that are strong enough to keep the lizard on the surface. So that's one of the reasons that the lizard usually keeps moving, because friction creates their charge, and this charge interacts with the wall and keeps the lizard from falling. Okay, so to finish this chapter and move on to the next one, let's think about one thing. What happens with the boiling point of the water if we add sodium chloride to it? Why? So let's think about that for a couple minutes, and then let's start the next chapter. Would you expect the boiling point to increase, decrease, or no change? So let's think for a couple minutes, and then we will move on to chapter number 11. All right. So what should happen with the boiling point of the water if we add sodium chloride to it, and why? So with that question in mind, we will start chapter number 11. Okay, so let's talk about solutions. And let's talk about the effects of adding, for example, salts to the boiling point and the freezing point of solvents. Very short chapter, so we will talk very quickly about vapor pressure and colligative properties of solutions. Remember here the order and magnitude of each intermolecular force. So dispersion, followed by dipole-induced dipole, dipole-dipole, hydrogen bonding, ion dipole, and we can have higher here ion-ion as well. So let me start with vapor pressure. Vapor pressure is defined as the pressure exerted by a vapor when the vapor is in equilibrium with the liquid or solid. So let's see how that works. So imagine here that we have a closed flask and we filled this flask with, for example, water. Let me go back to the other screen for a second. Okay, so what should happen with the water molecules when they are in a closed flask? Because the system is dynamic, the water molecules are moving in a chaotic motion, and some of the water molecules, especially the ones at the surface, they have enough energy to escape from the liquid and move on to the gas phase. Okay, so we are moving here from liquid to gas. And let's say another molecule is also capable of moving from liquid to gas. So this is called evaporation, and it happens all the time. So if you leave a wet cloth on the outside in a warm day, after some time it will be dry because of the evaporation process. Okay, some molecules, especially at the surface, they have enough energy to escape the liquid and become a gas or becomes a vapor. The amount of molecules that are capable of escaping from liquid to gas is proportional to the vapor pressure. Okay, so when the molecules are in the gas state, we can assume that's an ideal gas, and the pressure of the gas is going to be proportional to the number of molecules. If we increase the temperature of the system, we are increasing the energy. Now, all of a sudden, more molecules are capable of escaping the liquid and going to the gas phase, which will result, of course, in an increase of the vapor pressure. Okay, so therefore vapor pressure tells us how easily molecules pass from the liquid to the gas state in a given compound. So that depends, of course, on the temperature. So we can build graphs for vapor pressure as a function of the temperature in a given condition. And we can go to the tables and look up what's the vapor pressure for any kind of solvent. Okay, so see here in the table, we have vapor pressure of water, acetone, and methanol, for example. So water has the lowest vapor pressure, followed by methanol, followed by acetone. So that means at the same temperature, there are less molecules of water in the gas state when compared to methanol or acetone. And again, that's a reflex of the intermolecular interactions because each molecule to escape the liquid state has to overcome the intermolecular interactions. More intense the interactions, lower the probability to escape the liquid and move on to the gas phase. So that's why water has the lowest vapor pressure, followed by methanol, followed by acetone. Okay.
Can can the pressure of the atmosphere affect vapor pressure?
Professor, I think someone asked a question.
Okay. Oh, dang it. Yes, I cannot hear you guys. So if someone has a question, can you please type on the chat? Okay, so Katie, thank you very much for your question. And the question is, can the pressure of the atmosphere affect the vapor pressure of a liquid? And the answer is yes, it can. Okay, so let me see here. If you have a stronger, sorry, a higher atmosphere atmospheric pressure, sorry, you are compressing the system and you are creating a stronger resistance for the molecules to move from liquid to gas. Therefore, vapor pressure is dependent of the pressure of the atmosphere and the temperature. Okay, so lower pressure, there is low or non-resistance for the molecules to move on from liquid to gas. I hope that answers your question. All right. Okay, so let's go back here to the PowerPoint. All right, and let's move on. Okay, so now let's talk about colligative properties of solutions. Colligative properties of solutions are properties that depend upon the concentration of solid molecules or ions. For example, vapor pressure lowering, boiling point elevation, freezing point depression, and osmotic pressure. Okay, so let's start with the boiling point elevation. So let's start with water, and let's imagine that we can see the water molecules. So the blue sphere is the oxygen molecule, and the white ones are uh, hydrogen molecules. Okay, so remember that the evaporation is basically the movement of water molecules that are in the liquid that have enough energy to escape the liquid and go to the gas phase. To go from the liquid to the gas phase, the molecule has to break the intermolecular interactions and escape from the liquid. And in the case of the water, is the hydrogen bonding that has to be broken. What happens with the boiling point when we add a sodium ion to the water? So now the water molecule or molecules, they have to break the hydrogen bonding and also the ion dipole interactions. Okay, so we are adding here an extra interaction that is even stronger than hydrogen bonding. What what's going to be the effect of this new interaction on the boiling point? Is going to be easier or harder to leave the solution now? Because we have an extra interaction that's really strong, now becomes harder for the water molecule to leave the solution. Therefore, we need to provide more energy to the system to boil, which results in an elevation of the boiling point. So every time we add a salt in the water, and this salt is soluble, we will cause an elevation in the boiling point. What about the freezing point? When a compound freezes, it goes, of course, from liquid solid to solid. Therefore, we have to shrink. Okay, so the molecules, they have to get closer together in a more compact form. When we have sodium plus dissolved in water. Now we added an extra interaction that's called ion dipole interaction. This interaction will hold the water molecules in place and it will become harder to solidify. Therefore, we have to go colder to freeze water with salt, and that causes the freezing point depression. So, to summarize, when we have a salt dissolved in water or a solvent, that will result in a boiling point increase because of the stronger intermolecular interactions and freezing point depression because of the strong intermolecular interactions. And that's called a colligative property. Okay, so at this point, I need you to understand why there is a boiling point increase and a freezing point depression. Okay, it all depends on the intermolecular interactions that you have. More interactions and stronger interactions will cause a more dramatic effect in the freezing point or the boiling point. So you need to understand the chemistry behind the observation. So that's always the first step, and that's what I need you to understand. Of course, we can always do some calculations, and that's what I'm going to show you in a minute. Okay, so in areas where we can have snow, it's very common to salt the roads. Okay, so the idea behind throwing salt on the roads is that now we have salt dissolved in water that will cause depression in the freezing point and will melt the ice. Okay, and that will become water. Of course, if it is too cold, we have to add more salt. Some places also add sand. The sand does not have any effect in the freezing point depression because it does not dissolve in water. So the sand is there just to create more friction between the tires and the road and improve the dirigibility of the cars. Okay? The real factor to melt the ice is the salt. Okay, so to finish that chapter, let me show you a couple equations. So we can calculate the change in the boiling point when we add a compound to, for example, water. And we can do the same thing for the freezing point. The equations are very similar. So we have for the boiling point elevation, delta TB, and delta TB is the difference between the boiling point of the pure solvent compared with solvent plus compound. Okay, So that's delta TB. Delta TB is going to depend on the Van 't Hoff factor, I, also on the boiling point elevation constant, Kb, so that is tabled for all the solvents, times the molality. Attention here because it's not molarity, it's molality, and it's represented as a lowercase m. So molality is another way to express concentration, and it is calculated by the number of moles divided by the mass of solvent. The difference between molality and molarity is that molarity is the number of moles divided by volume of solvent, while molality is the number of moles divided by the mass of solvent. Molality is preferred in these cases because the mass of solvent does not change as a function of the temperature, which can happen with the volume. Okay? Therefore, molality is a more trustable way to express a concentration. Number of moles of solid divided by the mass of solvent. The unit here is going to be mole per kilogram, or also represented as a lowercase m. For the freezing point depression, the equation is almost identical, except that now we are going to use the freezing point depression constant, Kf. Okay? And we still have the Van 't Hoff factor and the molality. So now what I would like to cover here is the Van 't Hoff factor. Because the delta TB and the delta TF depends on the amount of ions in solution, we need to use the Van 't Hoff factor to correct for that. How does that work? The Van 't Hoff factor is basically the number of ions generated in aqueous solution. For example, when we dissolve sodium chloride in solution in water, we are going to produce sodium plus and Cl minus. Therefore, the Van 't Hoff factor for sodium chloride is going to be the sum of the number of ions. It doesn't matter the charge. One cation, one anion, the Van 't Hoff factor for sodium chloride is 2. Now, what would be the Van 't Hoff factor when we have sodium sulfate dissolved in water? Attention here, because now we have 2 sodiums in the formula, so that's going to result in 2 sodium plus and 1 sulfate ion. Now, the Van 't Hoff factor for sodium sulfate is going to be 2 cations and 1 anion, therefore 3. See the difference when we have more ions in solution and the reflect of that on the Van 't Hoff factor. Therefore, more ions in solution, stronger the elevation of the boiling point or the freezing point depression, because now we have more ions to interact with the water and hold everything together. That's why the Van 't Hoff factor is important. Again, The Van 't Hoff factor is the number of ions generated in aqueous solution. So you have to know how to split an ionic compound. Higher the Van 't Hoff factor, higher the effect on boiling point or freezing point. The reason for that is that we have more ions in solution. Okay, so with that being said, I think that's the end. So good luck on your finals and thank you for the semester. Not the ideal setting, but we did it. And good luck on your degree. If you need something, just send me an email and I will be happy to answer it. I hope you have a good winter break and uh, good luck on your finals.
Thank you for everything this semester.